Hello, everybody. My name is Zachary Isreil, and I'm here with my partner, Kevin Hernandez. And we were funded through the NASA BP REU program this summer to work alongside the Air Force Research Laboratory Scholars Program in researching deflected forebody airframes, i.e., bending the nose of a missile, to see if we could get any better aerodynamic effects out of that.
So an introduction and motivation for our project. A recent United States Air Force Academy unpublished project looked into articulating nose cones, which have been shown to increase performance of a missile. They found that their articulating missile did have performance increases, but unfortunately, their results had a great deal of uncertainty. Our goal was to perform a similar experiment with a similar model, but to lower that uncertainty to get more conclusive results. Our model was capable of 0, 2.5, and 5-degree nose deflections. Along with that, our model had a fin and finless configurations to study possible fin effects and interactions. We tested at the polysonic wind tunnel in the AME building here. Regarding air reduction, our tunnel has a 40% less air than the Air Force Academy tunnel, and that's without implementing a better methodology for air control. Over our 2-week testing period, we tested at Mach 2 and Mach 4, and the experimental techniques we performed during testing. We used a 6-component internal strain gauge, which was used to capture the forces the model experienced. And we used oil flow and shadow graph techniques to visualize the flow field the model experienced.
So the greatest joy of this summer project was actually learning to set up and run the polysonic wind tunnel. So the tunnel engineers, Alex Carnes and Ben Keppel, guided us greatly in physically configuring the tunnel, which we initially did by using the overhead crane to install the Mach 2 nozzle block. And then afterwards, Ben was of great help installing the force balance, which is a very expensive piece of equipment and requires some pretty extreme wire routing through the roll mechanism and the pitch mechanism. We then learned how to configure the tunnel for shadowgraphy by aligning the mirrors and light sources, and then learned using their in-house software how to initiate and monitor data acquisition during tunnel operation. We were shown how to use their, again, in-house MATLAB code that produces safety plots for each run, ensuring that our startup and shutdown conditions never endangered the tunnel or the bridges in the 6-component strain gauge. When we moved into oil flow tests, we were again aided by the tunnel engineers. We removed the force balance and then installed black lights and slow motion cameras around the test section. And we used these to gather a 360-degree baseline view of the model, then ran the test and did another 360-degree view post-test so that we could see how the oil flowed. So over these 10 weeks, we deeply broadened our understanding of aerodynamics, the aerodynamic coefficients that we were looking for, what variables those were calculated from, how the tunnel calculates those. The emphasis that we placed on error reduction and data reliability is something that we don't get to see in the classroom setting ever. And so we had a lot of help from our graduate student mentors, Noah Moffett and Robert Smith, in implementing error controls into our experimental method, as well as doing error propagation analysis afterwards. The facilities that we got to use were second to none. The polysonic wind tunnel is the #1 wind tunnel in the public university system. And so being able to operate that was a massive joy and a fantastic experience. As for our results, during the experiment, we found that deflected forebodies will indeed increase lift-over drag and the pitching moment, which increases maneuverability. And we found that these effects will scale as the Mach number does. A very conservative upper bound for our error in our data was calculated to be 8.5%, which is fully 1/3 of what the Air Force Academy's unpublished papers error was. We would like to thank the NASA MUREP program and the Air Force Research Lab for funding our research this summer, as well as thank our graduate student mentors, Noah Moffett and Robert Smith, with huge thanks to the polysonic wind tunnel engineers, Alex Carnes and Ben Keppel, for instructing us in the use of their very, very expensive machinery.
We'd like to extend further thanks to our AFRL mentors, Ron Taylor and Craig Franks. We'd like to thank Dr. Shi and Dr. Moore for guiding us through the summer program. And finally, we'd like to thank Dr. Kumar and Dr. Gustafsson from FCAP for their help with data analysis.